And they can't take it that the interaction is so fast and what they call non-local. It doesn't propagate. It really doesn't take time to go anywhere. It doesn't go through anything. It does nothing you can affect it with. So it must be affected by something, and made various predictions of what it might be affected by, and then would propose experiments that you would have to do to check out whether or not this magic force was doing the slightly different thing they wanted it to do than to be perfect, okay? And these experiments that have been proposed never work so far. Now you say, oh, well, I can certainly invent one which works over the entire range that's so far been checked, if I'll tell you what it is, right? You can just make the rules so that it'll go further on, that it'll happen only 1 light year apart. You've got to move these a light year apart or you'll never see any effect. Okay, we can't do that experiment. It's still possible. You could have it if you wanted, but there's no evidence for it. And all attempts of this kind to make those suggestions, which were not stupid, because this is so peculiar, it might have been that the prejudice about the way the world worked that you had previously was in fact right, and that there was some delay in the interaction. It's a good suggestion, only it isn't so far true. So what we do in physics is we take what we find so far and try to extrapolate it to see over a wide range of experience to see if it works. It's always possible that the theories be wrong, that there really is an interaction, that this really doesn't work, what I told you with the 2 boxes when they're a light year apart, or some other distance. It's always possible. We're not trying to find out for certainty what the world is like, but just what we've seen so far. And we can summarize everything that we've seen so far by saying that this interaction is instantaneous and magical and does exactly what we want to get the answer over here, okay? And so we just don't worry about it yet, because we have seen no effects on various things. People, however, are aware of the possibilities and are making suggestions for experiments, but so far all of those experiments have failed. My personal opinion is that they're all going to fail, that the logic is wrong, that there was the prejudice that you had, a rather deep one, of course, about the potentialities for what's going to happen before you push, that must mean something, that the chicken in or out of the icebox has got to mean something. There's the only 2 possibilities, but that logic is wrong. I think that's really the way the world is, that our ideas that came from experience in the large-scale world are that wrong. That's all it is, but that's an opinion held by most physicists and perhaps incorrect, but we'll find out someday if the thing doesn't work. So far it works. So let's talk about so far, okay?
Would there be a way of changing logical?
I'll show you how we have to think logically, yes. Yes. We have to just be careful not to make some statement like, see, it isn't the fundamental logic, like you say, I'm going to assume a variable x can have 2 values. That's not what we're saying. We're saying there is a piece of chicken in an icebox or else it isn't. But we're not going to start to talk about what's in unless we open a door. Such ideas may not mean anything. It may not be an inside to the icebox, much less whether it's lit or not. As soon as you close the door, there's no inside, or whatever. So it's not logic, it's a question of what you're going to allow yourself to talk about.
So you're being rigorously operational.
Yes, it has to be more operational.
The other point that the uncertainty principle makes causality irrelevant. Because since you can't determine the present...
No, you can. If you measure whether this is a red light or not, it's perfectly all right. It's just that attempting to measure another thing about the present simultaneously changes what you found before.
Yeah, but you have to know where you are and where you're going in order to determine whether...
Yes. To determine exactly. But you remember I said that there would be probabilities, that we're not able to predict the future exactly. We only predict the probability of different events. And if you want to say that, you see, we're not in a situation where we know this present and that determines exactly the future, because it's not the way it appears to be. We can set up the present as perfectly as we want, and the future becomes uncertain. It's only probabilistic. So it's consistent with the thing. Now, just to continue with this identification of words, all right? It was Einstein, after Heisenberg talked about the uncertainty principle of position and momentum measurements, most physicists understood it and everything okay, and took this point of view. But Einstein and Podolsky and Rosen didn't like it particularly, and they wrote a paper saying they didn't like it. And that's what it amounts to. What they didn't like, they took the analog of this experiment, except for position and momentum measurements. They pointed out it was possible to get two particles separated. So by measuring the momentum of one of them, you would know ahead of time by the correlations that that would determine the momentum of the other. Just like if we push this button here, it would be just equivalent to pushing that button there, because they're always agree. So you could make a pair of objects so that the momentum of this would always agree with the momentum of that. Actually, the momentum were opposite directions, but that's technical. You could put it through a mirror. So you could make it so the momentum of this would always be the same as the momentum of that, and the position of this would always be the same as the position of that. So you measure the momentum of this one and the position of that one. And that was against the uncertainty principle, they said, because by measuring the position of this one, surely you can't be changing the thing over there. That Heisenberg would have said in the older way of speaking, if I would be crude, that by measuring the momentum, you jiggle and make unpredictable the position because of some mechanical effect. We have to deny that now. We can't just say it's a mechanical effect, as we've now noticed, that we can't say it's easy to understand that if you push this, you might have some wheels turning to change that. But if you push this, you have wheels turning over here to change that? No. So they just pointed out this little difficulty that you can't take the classical point of view that a particle has a position. Well, that if you measure the position, that there is a position of momentum, when you measure the momentum, you change the position. That's too crude, because you can measure the momentum of this other one, and it won't change the position of that one. This is a completely analogous. It's an example of an Einstein-Podolsky-Rosen setup. The idea is that by measuring over here, where it's practically inconceivable that this could be affecting that, you can determine what this would have been if you didn't push it. But we don't like to talk about what it would have been if we don't push it anymore. That's the way we escape from that. And it was already known by the time Einstein and Podolsky wrote that that was what people were saying. But they were objecting to that, and they said that that's not an adequate description of reality. Perhaps it's not an adequate description of reality, but it's an adequate description of whatever we're able to predict. And people who've tried to increase the reality of this by making this a real wave or something like that have always produced predictions which don't agree with experiment. So that's where it stands. And that's, now we've talked about the uncertainty principle, and Einstein, Podolsky, and Rosen. All they said was there was such a situation, which we've already used. Did you have a question? Yes.
I've always been impressed by the fact that I've not seen very many comments on the philosophical premises laid down by EPR, which is if I can predict something with complete certainty, there's an element of reality that I can attribute.
Yeah.
And basically what you're saying is that's the piece of the action that you have to let go of.
That's right.
Create the dilemma.
That's right. You got that. Yeah, just because I can measure, yes, right.
Classical reality
Finally,
is fixed, and this reality is not.
it's a different kind of reality. The world has to look different. Yes.
Is that partially what you were saying too, that it's not a matter of the logic yet, that we haven't gotten the new logic, but that right now we have to let go of the assumptions or other ways?
Yes. There are two ways always of doing it. When something doesn't work, you can either say that you're not allowed to make certain steps of logic, or to make certain perfectly obvious assumptions that look perfectly reasonable. Both of them are difficult because we don't like either of them. The logic looks good. There's two ways of doing it. The easiest way, and the way that we've all chosen for practice, is to say you can do as much logic as you want, but you've got to be very careful about the kind of assumptions that you make about what's real and what's there, especially about potentialities. The whole thing is summarized this way. You can't say that this thing has the potential for producing red, green, and green. That's there before you push to check it. Okay? Wheeler has said, in a way, it's one of these beautiful aphorisms that are shorthand, which you can only understand after you've finally understood the whole. Oh, you want me to wait a minute for your tape? Okay? Wheeler has made one of those lovely aphorisms to describe this, which you'll only really understand thoroughly when you understand the whole thing. But it helps to remember. He says, there's no phenomenon. A phenomenon is not a phenomenon until it's an observed phenomenon. In other words, you can't tell what's happening in there, or there's no chicken, or there isn't chicken, until you look to see. So you only talk about what you can look to see.
No, it's the forest.
Wheeler, John Wheeler.
Who said
Oh,
we're away from probability and seeing the returns?
I don't know.
Isn't that Wheeler?
Maybe, I don't know. And then finally, in the list of things that are in the prospectus for this workshop,
Taking care of,
there was Bell's theorem. Huh?
taking care of all that business.
Yeah, I want to take care of the business. I advertise something, and I have to show you that I've already done it. The other one is Bell's theorem. I've already told you about that, I think, and that says is simply a mathematical statement of the fact that situations like this can arise, where the actual probabilities observed are impossible to explain by a classical type of card-filling boxes scheme. If the odds had been 2/3 that we would get a different color and not 3/4, we could have explained it easily. With all this logic would be okay. But that in quantum mechanics, some of the probabilities that would be predicted by quantum mechanics would disagree with the simple arguments in a situation like that, like this, that you get by thinking about cards being in the boxes. In other words, quantum mechanics would produce effects like this. The mathematical theorem is more complete. It tells you how much the effects are and where to look for them. But we have an example of such an effect, and that's all we need to show that something, that quantum mechanics is odd. You don't also need a theorem to tell you how odd it's going to be in every case, which is what the theorem was. Okay? The theorem was in fact inspired by such discussions of this for special examples. And not quite as simple as this one, where we have only 3 measurements, but measuring spins of electrons that were correlated and so on, where you can measure something that has light, or the polarization of light, where you can measure a whole lot of different possible places. It's if we had boxes with lots and lots of buttons. The point would be that some of the odds on the buttons were against the common sense, old-fashioned common sense. Yes.
I was just going to point out that actually Bell's description is very much like this description in the sense that in his setup, you actually do have to look at 3 different polarizer settings in order to get the inequality, just as you have to have the 3 buttons.
You need at least 3 before you get into trouble. You can show that there's no situation where you can measure just 2 things where the probabilities are not something that you could imitate with cards. So that's why it involves 3 in his theory.
Nice parallel.
Yes. We're there because, yes, where the thing is done general, or you have a special example, there must always be a parallel between a general theorem and the special example of a kind. In fact, I personally find different people are different. Some people think abstractly right away very well. I don't. I always have to have examples to understand something the first time I hear it, and then I kind of generalize from the examples. Other people like the general thing and then try to use it on examples. So I like this way of thinking of things, a nice, simple example where all the things are perfectly clear and there's not a lot of mathematical stuff that confuses me. Which if I study hard, I can sort of check out. In fact, what I do is the opposite. I take the mathematical scheme and try to find a case like this. I didn't find this one. I found one with 6 buttons. Okay? I mean, my original one was more complicated than this one of Merman, which is beautiful. Beautifully simple. Mine had 6 buttons. It was almost the same, actually, but it wasn't quite as good.
Can you give us a practical application of Bell's theorem, the way you talk about the sunset and the moon? And
No.
No.
No, we've talked about it. There's nothing magical about it. It's just a mathematical statement that there are situations in the world where you make measurements like this, which will have this kind of paradoxical probability answers. You know, the answers will be not understandable by supposing it was done with cards that were shifted and stuff like that. Okay? That this kind of a thing can happen. That's all it is. It's a statement that this kind of a thing can happen.
Who added this non-local reality idea?
I don't know about non-local reality. What?
2 sets.
Huh?
You mean the 2 sets of different, 2 sets of 3 boxes?
Right.
Well, Einstein, Podolsky, and Rosen are the ones that emphasized this kind of a situation. It was already known to others what would happen in this situation. In fact, they could use the mathematics of the theory that existed for this kind of situation, but they didn't like the result. And they simply said that. They said, can quantum mechanics be a complete description of reality? Because, as you pointed out, they made an assumption about reality, which was that if you could determine what was in that thing, that had to be somehow real. And if you could determine by doing something over here which didn't affect that, it couldn't affect that because there was no no independent of distance and simultaneous and so on, then that was somehow real there, and they wanted to make it real. They insisted, in other words, that we be able to say that there was some sort of potential cards in here that are determining what happens. And that's just what we don't say. So, yes?
Yesterday you described that if you go through this process of pushing number 1 and it's red, then you push number 2 and it's green,
Yeah.
and you push number 1 again, it could be red or
Right.
green. But now if you go to the second box,
Right.
it still hasn't changed number 1.
Correct.
Although number 1 here may have been already changed. Would that preclude any forces between them in any operating? Because
In
obviously...
a kind of way it does, doesn't it? It means that, yes, that's true. That if you were to say in some mechanical way that when you push this, you'd change that, then you would think that if you kept pushing the other ones, it would keep changing that, okay? But it doesn't. Any further actions over here have nothing to do with what happens there. The only thing this is good for is permitting you to know what you would have gotten if you pushed, or rather, better, I should be careful, permitting you to predict what would happen if you pushed the same button, period. That's all it's able to do. After that, the first time, and after that, nothing. That's an interesting point, and I have not analyzed that very carefully, and I don't know what the people who invent these waves have done with that aspect of it, okay? Why it disappears after the first measurement. It's an interesting point that I have not studied. Thank you. I'll have to look that up, into that. So that sort of helps to make it impossible. It makes these waves get more and more complicated. To explain what? A result which we can describe over here and forget about this if we wanted to. It's just that this is correlated with it. Okay? So, I guess that takes care of all of the 3 things. Okay, now I've sold you what I advertised. And now I would like to, well, we're not finished yet. Okay, we can talk about a few other things. And that's this. Let me ask this question. See, you don't know what can be done and what can't be done, so I'm going to tell you something. Maybe we could make a copy of this box without bothering it. That is, we can make another box over here. 3 boxes. Ooh, what a wonderful idea. 3 boxes. And let's make it so that, is it possible? This also has a 1, 2, and 3. Is it possible to make 3 boxes such that the following happen? That if I wanted to find out what this would do, I remember last time with 2 boxes, I could push that. If this is red, that'll always be red. After or before. Make it 3. Then I could push this one also to determine whether this would be red. For example, if this is red, then this is red and this is red. Can we make it work with 3? In other words, in nature, is it possible to arrange that there are 3 boxes which have the following property? I could look at any box to determine whether this was red by pushing any one of those buttons, not necessarily this one, and they'll always agree. All 3 boxes always agree. Likewise, if I push button 2, all 3 boxes would always agree. Or if I push button 3, they would always agree. Then we were going to get in trouble. Because it takes a little thinking. I haven't thought it out to make it simple. But because we have another box by which we could make another measurement over here, so to speak, without touching it, we're going to find it's impossible. Now, it's not impossible simply because it's logically impossible, but, I mean, it's logic. But if you count the number of cases that you get, that is, you measure this box here, and this box here, and then ask how many times the pairs differ. They have to be a third. You see, this time I would be able to make 3 measurements, and I could list the 3 measurements. I could tell you what was 1, what was 2, and what was 3. Now we would have, maybe it would turn out that one time it would be red, black, black. Those were the results, or green, green, I guess. Those are the results of measuring 3 different boxes. They're all available. Another time it could be green, red, red. The 3 different boxes, or maybe red, red, red. Because I have an experimental situation with 3 boxes, and I push 1 button on one, button number 2 on the second box, button number 3 on the third box. So this is number 1 on box 1, or box A. This is number 2 on box B, and this is number 3 on box C. There's nothing wrong with that. So here's the 3 boxes, A, B, and C. And remember that whatever I get on C would be of the same if I pushed it on A, same number. Now if I make this long list of possibilities, which are all measured now, those are numbers that are in notebooks, they're not in boxes anymore. I pushed the buttons and I wrote the answers down. Okay, after I've done this for a week and I've got thousands of these, I go back and I count. Nothing, has nothing to do with the boxes, nothing. I count how many times do I get out of all this a pair, one pair equal and one, I got to get at least one pair equal out of every 3. See, I could think of all the, I just have to count, let me see, what do I count? I count how many times a pair that match appear. And here's one, it depends. How many times, okay, let's say how many times a pair match appear in the column 1, 2, plus how many times a pair appear in the column 1, 3, or how many times in 2, 3, and I've counted all the pairs. And you see there can't be any less than 1/3 that pairs match. This is a pair that matched. In this case, these didn't. In this case, this pair matched, but the other two didn't. So I must get at least 1/3 matches. I can't get only 1/4 matches because I've written them down. I mean, that's impossible. So it's impossible. Therefore, something would be wrong if I could do it with 3 boxes. And nature doesn't permit us to do it with 3 boxes. It's not possible to arrange in quantum mechanical world, in the real world, in other words, 3 boxes which have this property that if I push any one button here, I can determine what the others 2 would do. Any button. All right? What is possible, it's curious, what is possible is to arrange 3 boxes such that they all agree with hole number 1, say, for instance, button 1. I can take 3 boxes. In fact, I can take 3,000 boxes. I can make as many boxes as I want. Let's take 3 first, because you get nervous. So if I push button 1 and say it's red, it'll turn out that any of the other boxes, if I push 1, it'll also be red. Right? All right? But if I push number 2 on this box, and it's green, say, it doesn't mean that it's green here, or it's green here. It doesn't agree in general, necessarily, all right? You understand? I can make it so that this box will agree with all the other boxes if I push 1. So I can use any box I want to predict what 1 is going to do on any of the other boxes.
It was the first one.
Number 1 box. I got a special arrangement. I made a special arrangement with the number 1 connection system, yeah, where I make multiples of these boxes, say 3 in this case, or 5 if you want, but which have the wonderful property. Let's make a lot of them, okay? I keep doing this. You can go to 3, 4, 5. I'm jumping too fast, but you can, it's the same idea. And I have a lot of boxes, and it's possible to arrange it by, possible to get things set up. It's first position. No, first button. First button and first push. No, any number of pushes. If you just, if you don't push.
And it came green, would all the rest of
No.
and 2 C's, the first push, be green?
No, let me say exactly what happened. You're probably guessing right. Let me just say it then. Now, you push 1 here, and it's red, let's say. Then you can predict that if you push 1 here, it'll be red. If you push this one, it'll be red. If you push this one, it'll be red if it's number 1 hole. Okay. However, right, if you push number 2 now, or push 1 here and 2 there, you can't predict what it's going to be, but 3/4 of the time you can guess it'll be different. Okay? Nor can you predict what will happen on this one. They won't agree. In other words, let's say I push this red, I got red, I look in this box, I push this when it's green, okay? This does no longer have to agree with this. I can push this, it wouldn't help me to know what this is, and pushing that after I pushed 1 doesn't do any good. Nor, in fact, is it true this way, that if I started this out and I know they all agree in 1, by pushing 2, I can find out what I would get on the others. No, I'm not allowed to do that. If I do that, I'd get in trouble, as I told you, because I'd make a list and I would be in trouble. A different kind of trouble, much worse, because it's on a notebook. But there it is. I count them, and it's impossible. Yeah.
You say it's only the left-hand position.
Yeah, for instance, you could make it for the other positions, and you can make other kinds of correlations. But now let's say it's possible to make a perfect correlation, but only for 1 position. Okay? A perfect correlation means that you can determine any other box by pushing 1. You can only do that with 1 position. You can't do it with more than 1. When there were only 2 boxes, we had the wondrous fact that we could do it with all 3 positions, correlated perfectly, but no longer, not when we try to make multiples. In fact, if you made multiples that have this property, that are all built, so you're guaranteed they've been built by the same process all the time, so that number ones all agree, which I'll call number 1 correlated boxes, okay? If you arrange to make a large number of number 1 correlated boxes, and you don't push number 1, okay? But you ask yourself, what happens if I push 2? Let's say I push 2 on this box, it's green. And I push it on this and I record it. I push it on this and I record it. And I make a whole record of all the green, all number 2s. You know what's going to happen? Not all green, no. Because if they were all green, then they would agree, and I said I can't do that, or I'm going to get into trouble.
3/4.
Yes, sir. 3 of one kind and 1 of the other. And which kind? After you determined for a number of these boxes, let's say you had 1,000 boxes, and you used 900 to determine what it was, and it was 3/4 of the time green, then you can guess. If you push this button on the other ones, it's red. And they all agree. They've been loaded. Okay? You can even determine what that is by measuring the others and measuring probability. But only by probabilities. All right? This correlating many copies on the same thing is what's really called measurement. Because when we measure something, we're able to make records and write it down somewhere else, so that if we wanted to get the answer, we can look at the writing. So making a copy is analogous to making a record. I could play around with these boxes and throw them away, and still find out what this one was by measuring this. Any one of the boxes, they'll all agree still, the ones that are still left. So this copying process, in this particular case, a copying process which sustains the correlation in hole number 1, or button number 1, is called measuring what the result of 1 is. And the measurement of 1 precludes a perfect correlation in 2. It insists, if you've made such a thing, that number 2, that's 3/4 of the time green and 1/4 of the time red. It's saying the same thing again. Instead of making the same button measurement on the same box all the time, just making many copies. Yes?
I would suggest don't always use box number 1 as the first button you push, because then there's the possible confusion
Between the box
the
label?
location of it and the fact that it was the first button you pushed.
Oh, I see. Oh, you mean using 1, 2, and 3, I push button 1, you might be confused with whether it's the first button I pushed. In time, you mean? First in time or first on the box. Well, I'm sorry that I made that error. We could have called the buttons a PQR or something. It would have been better. Or the left button. That's a better idea. The central button and the right button. Good. Okay, that's better. Now, if there was any confusion, I'll say whatever I wanted to say again. I've arranged things so that the left button is correlated. If you push it on any of the boxes, the left button will give the same answer as on any other box. Thank you.
No, right, because it's still the same problem.
What?
Instead of say initial, don't you think the
No, what?
initial request?
What's the problem? I don't understand it.